For the second part of the video, we'll be discussing equilibrium constant expression. And for this video's objectives, at the end of the video, should be able to set up a chemical equilibrium expression of irreversible reaction, solve for the equilibrium constant, as well as interpret the magnitude of the equilibrium constant. Okay, so let's first define equilibrium constant expression, also termed as equilibrium constant. Okay, so when a reaction is at equilibrium, we'll have a constant amount of reactants and products. And if we compare the concentrations of those species in terms of ratio, okay, we'll get a constant value, which is the equilibrium constant. And this is based on the stoichiometry of the reaction. So stoichiometry still would rule everything. Okay, so example, we have this hypothetical reversible reaction wherein A and B react to form B and E. But B and E are also reverting back into A and B, okay? So A and B are in chemical equilibrium with B and E. Now, if we are to write the equilibrium constant of this, or equilibrium constant expression of this reaction, then we can write it as Kc equal to the products raised with each of them raised to their coefficients over the concentrations of the reactants, each raised to their respective coefficients. We can also write equilibrium constant expression in terms of Kp, which is in terms of P, or pressure. Okay, so the equilibrium constant can be in terms of the molar concentration or in terms of the partial pressure. Okay, so facts about the equilibrium constant. Now, the equilibrium constant is a unitless number, so we don't associate units with that. It's just a number. And for each reactions, they have their unique equilibrium constants. Furthermore, they have identified that the equilibrium constant is temperature dependent, meaning for a specific type of reaction, the equilibrium constant will change depending on your temperature. Okay, and now in terms of interpreting the magnitude of KEQ, we say that if the K is large, okay, you can already predict based from the previous slide, right? You have the product over reactant there. If the K is large, then we could say that the products predominate. Okay, the products are favored, or we could say the equilibrium lies to the right, since the products are written to the right of the arrow. For small k, we say that the equilibrium lies to the left, or the reactants predominate. So let's have the sample problem. We are to write the equilibrium constant expression of the reaction of ozone in equilibrium with O2 or oxygen. So remember, you have product over reactant. So to write that, you have the product O2 over the reactant O3, each raised to their respective coefficients. For O2, its coefficient is 3, so that becomes its exponent. And then for O3, its coefficient is 2, and it becomes its exponent. So as simple as that. We can also write in terms of pressure, right? Okay, since this is in gas form, so you just change in terms, instead of concentration with a bracket, write it in terms of P, partial pressure. But still the same, partial pressure of O2 raised to 3 over partial pressure of ozone raised to 2. Now, if you're wondering why can we use Kc and Kp for this particular reaction, now, the equilibrium constant in terms of concentration can be used for both aqueous and gaseous reactions. Whereas the equilibrium constant in terms of pressure can only be written for gaseous reactions. Since this is a gas, okay, ozone and O3, ozone and O2, then we can use either Kc or Kp as our equilibrium constant expression. Moving forward, okay, we have this second example. Cadmium and bromine in equilibrium with the complex CdBr42 minus. And since this is in aqueous form, we can only use Kc. Okay, so you have the product over all the reactants multiplied together, but each one are to be raised to their respective exponents, which comes from their coefficients. Okay, how about this? You write the equilibrium constant expression for the reaction. You have titanium and chlorine in equilibrium with titanium chloride. Okay. So for this particular example, I'd like to point out that we have solid, gas, and liquid phases here. Okay. And when we write the equilibrium constant expression, we are supposed to ignore all the solids and all the liquids. The rationale for doing this is that solids and liquids don't change their concentration, nor do they change their partial pressure. So solids would be pure, and liquids would also be just as pure. We don't write or we don't say that certain solid is dilute, certain liquid like water, this water is dilute. No, we only reserve those terms to solutions or to gases. So if you encounter reactions with solids and liquids, you ignore them. And thus, the equilibrium constant expression would be reduced to this one, 1 over concentration of Cl2 raised to 2. Okay, ignore product side, there's no gas or aqueous component, so we only have 1. Over, we ignore solid, we just write this one. Furthermore, since we're left with a gas we can't ignore, then we can also write the equilibrium constant expression in terms of pressure. Okay, so this is the last sample problem for this video. An aqueous solution of acetic acid, okay, which is present in vinegar, is found to have the following equilibrium concentrations at 25 degrees Celsius. You have 1.65 times 10 to the negative 2 molar of acetic acid. We have 5.44 times 10 to the negative 4 molar of hydrogen ion. And we have the same amount, 5.44 times 10 to the negative 4 molar of acetate ion. Now we are to calculate for the equilibrium constant of the ionization or dissociation of acetic acid. The reaction is written as this. And there's a follow-up question. What can you say about the reaction based on the value of K? Okay, so first we set up the equilibrium constant expression, product over reactant, and then we substitute the given values. Okay, note that we should substitute equilibrium values. It's stated here that these are the equilibrium concentrations. And then simplify, we'll get 1.79 times 10 to the negative 5. And this is a very small number, okay? So we can interpret this equilibrium constant as this. At 25 degrees Celsius, the reactants predominate at equilibrium. Or we can also say at 25 degrees Celsius, the equilibrium lies to the left.